Hello, today we're going to talk about electric potential. So we're going to start by defining electric potential. Another goal we have is to talk about the connection between electric potential and electric field. And then we will also talk about the connection between electric potential and electric potential energy. They sound very similar, but they are different things. They even have different units. So you have to be very careful to distinguish between electric potential and electric potential energy. They are different things, closely related, but different. Okay, electric potential. And one way to think about it is that it is related, electric potential is related to potential energy, the same way electric field is related to force. So field we can think of as the force per unit charge. That's one way to think about it. If we put a charge at some place where we know the field, then we get the force. If we know the force on a charge that's present, we divide by the charge, you get the field that is at that point that the charge is experiencing. Our symbol for electric potential is V. Potential energy, we're going to keep using the symbol U. And so potential, electric potential, is electric potential energy per unit charge. Okay, so in the same sense that E is F over Q, V is U over Q, they're related to potential related to potential energy in the same way that field is related to force. Now, a big difference between those things is that field and force are vectors, potential and potential energy are scalars. And in many cases, what really matters is what we call potential difference. So the potential difference is the change in potential energy per unit charge. And also potential difference is really what makes things flow, what makes charges flow. Okay, so what is electric potential? Well, it's similar similar to field in the sense that it is a way to visualize how a charge or a set of charges affects the space around it. Okay? So there doesn't have to be a charge at a point for there to be a field there. There doesn't have to be a charge at a point for there to be an electric potential there. Okay? If you want a force or you want a potential energy, you have to put a charge at the point where you're interested in. But field and potential exist at a point independent of whether there's a charge there or not. It comes from all the other nearby charges. Okay, and you've probably heard the term voltage, and a voltage is a difference in potential difference in electric potential. Okay, and if you have a pressure difference, you can make fluid flow. If you have a potential difference, electric potential difference, you can make charges flow. Okay, so what we have here is a contour map of the region around Mount Rainier in Washington State. There are a whole bunch of lines on this map. In a similar way, when we often have kind of a region in which there are some charges, we can draw a set of equipotentials. Now, equipotentials are lines of constant potential, and they're similar to these lines that are on this contour map here. So what do these contour lines represent on this map, which shows the vicinity of Mount Rainier? Well, they represent lines of constant height. In fact, if you look closely, you can even, well, probably hard to see in the movie, but if you look closely, you can see there's just a little bit above the T and the R in Mount Rainier, you can see a line that reads 13,800. So that would be 13,800 feet along that particular line. And then I think all these darker lines are 200 feet spacing. Okay? and the top is something like 14, 4, 10, something like that. Okay, so there is a connection here between field lines and equipotential lines, and we can think of it in the same way, that there's a connection between sort of the field on the mountain itself and these potentials. So you can look at where the lines are very, very spread far apart, and what happens there is that the height on the mountain changes very slowly at those points. There are other places where the lines are so close together that it just sort of looks like one line. There's a whole bunch of lines bunched together. It's incredibly steep at those places. There might even be a cliff at that location. Okay? So you got to take this into account when you're trying to hike up Mount Rainier, for instance. Okay? So you want to avoid these places where the contour lines really run close together, unless you're really into rock climbing up steep mountain faces. Okay, maybe you want to go for those places, but that's what it means. And similar things happen on a plot of equipotentials. Okay, now field lines are always perpendicular to equipotential lines, so what you see here is that equipotential lines run in a particular direction, and then if you go along an equipotential line, well, you're not changing height at all. Okay, so to change height most quickly, you go perpendicular to the contour line. Okay, so here's a special case of a very uniform field here. So these are the equipotentials. And there's one line labeled 0, there's one line labeled plus 10 joules per coulomb, another one plus 20 joules per coulomb. So these lines are spaced by 10 joules per coulomb apart. There's a few points here, A, B, and C, marked down. Okay, so there's a picture of equipotentials, and you're only going to get a set of equipotentials like that, so nice and spread evenly apart, if the field is uniform. Okay, now you can actually tell which direction the field goes from this diagram. Okay, so remember the field lines are perpendicular to the equipotentials. Well, that is a little ambiguous because perpendicular to these lines is either up or down. Now, it's one or the other, so how do you tell? Well, field points in the direction of decreasing potential, just like force points in the direction of decreasing potential energy. Okay, so decreasing potential is down in this picture, therefore the electric field in this picture is directed down. Okay, now note that points A and C are on the same equipotential. Okay, so you could actually move a charge from A to C, and doesn't require any work to do that because you're not changing potential. Whereas to go from A to B, you're going to need to do work. Going from C to B is the same as going from A to B, work-wise. And that's very similar to what happens in a gravitational situation. Okay, now this is potential we're talking about, and there is a connection with the field. So I think you can make this kind of quantitative connection. E is minus delta V over delta R. So what it really means is pick the direction in which you decrease the potential most rapidly, and that is the direction of the field. So in this picture, you want to, if you're at say you're at point B, to decrease potential most quickly, you go straight down. So that is the direction of the field at B. And note that joules per coulomb is the same as the unit volt. Okay, so if you want to measure potentials in volts, that is perfectly fine. Okay, potential difference. Now, in many ways, just like changes in potential energy were far more important than what the potential energy was last semester, same thing happens this semester. A difference in potential is way more important than what the potential is at a particular spot. So it's how the potential changes from one place to another. In a uniform electric field, well, uniform electric field, we get delta V is minus E delta R cosine theta. So let me talk about that in a minute. let's start with this equation at the beginning here. So delta V is delta U over Q. Okay, that's true all the time. Okay. Now delta U, that's a change in potential energy. Now a change in potential energy is the negative of the work. So this thing, minus F delta R cosine theta, that's work. That's in fact negative of the work. Okay, so in our case, the force is coming from a field. Okay, so in a uniform field, we can say the force is simply QE. And then the Q's divide out. Okay, so then you get potential difference is minus E delta R cosine theta. Theta is the angle between the displacement vector, delta R, and the field vector, E. So it's a lot of work ideas going on here. This is highly connected to what we did last semester in terms of work, where we could say delta U is minus F delta R cos theta. Okay, and I already said that. Theta is the angle between the electric field and the displacement, delta R. Okay, so often we just need the magnitude, and we often simplify this to delta V is just ED. And now D is not any old distance, it is distance moved parallel to the field. Okay, so E is the field, D is the distance you go parallel to the field, you're going to change your potential by delta V, magnitude-wise at least. Okay, depends whether you're in the sign, really depends on whether you're going with the field or against the field. Okay. Okay, now we could have done this last semester and talked about gravitational potential difference. We never did. Okay, but we can go back and define it. So it's the change in gravitational potential difference is the change in gravitational potential energy, mgh, divided by the mass, and then the masses cancel out, and you just get gh. Okay. So this is equivalent to the ED equation we get for delta V for electricity. Okay. So think about what GH represents. So every point in the room around you has a particular gravitational potential. The higher up it is, the higher the potential. Okay. As H increases, the gravitational potential increases. Okay, what does that tell you? Well, if you take a mass and you stick it at a point where it's got a higher gravitational potential, well, you let go from there, it has more kinetic energy when it hits the ground, when you let it go. Okay, now we're going to talk about potential from a point charge. And this is not a uniform field anymore. Okay, point charge gives you a non-uniform field. The other thing that happens is when your field is uniform, you get to pick the zero level for potential or potential energy. Here you do not. Just like we couldn't do with gravity when we went to minus gmm over r for our gravitational potential energy last semester. Okay, so if you go a distance r from a point charge, the electric potential due to that charge is given by this nice equation. V is simply kq over r. Okay, this will have a sign. It's the same sign as the sign on the charge. So if Q is positive, the V is positive. If Q is negative, the V is negative. Okay, so here we have a green ball at the center of this picture. The green ball represents some charge. There are equipotential lines that surround this charge. The one farthest out is labeled minus 4 volts. The next one in is labeled minus 6 volts. The next one would be minus 8, then minus 10, minus 12, minus 14, etc., etc. They get really close together the closer you get to the charge. And so it's hard to label them. In fact, they're so close together, it's hard to see that they're separate lines. And there's basically an infinite number separated by minus 2 volts. Okay? The closer you get to the charge, the more negative the potential gets. Okay. In what direction is the field in this situation? Okay, so let's think about that one. Okay, so here we go. Same question here. What direction is the field? So answer 1 is clockwise, 2 is counterclockwise, 3 is toward the center of the pattern, toward the charge, 4 is away from the center, that would be away from the charge, and 5, we just don't have enough information to say. Okay, so think about which answer you like the best. Okay, so now we're going to think about how to approach this. So in fact, what you remember here is that the field points in the direction of decreasing potential. So the minus 4 volt line is the furthest out circle that we see. And the next one is minus 6 volts. Going from minus 4 to minus 6 is a decrease in potential. So the field does point in the direction, in the inward direction, from minus 4 to minus 6, and then minus 6 to minus 8 to minus 10, etc. Okay? So that's one way to think about it. Okay, so points in the direction of decreased potential, that's toward the charge. Another way to think about it is that, well, we've got our equation. V is kq over r. The sign on the potential, V, comes from the sign on the charge, Q. Okay, so you recognize that here we have negative potentials, minus 4 volts, minus 6 volts, etc. The only way to get negative potential from a single charge is for that charge to be negative itself. And if you have a negative charge, field lines always point in toward that negative charge. Okay, here's another question for you. We're going to take a positive Q charge. We're going to put it at the start position, and then we're going to move it up a distance r to the end position. Okay, so it's got a size Q. It's moving a distance r. We want to know the change in potential experienced by the charge. Note that the start point is on the V equals minus 4 volt line. These are units of volts, in fact. And the end point is on the V equals 8 volt line. Okay, so again, this is a uniform field scenario, and you've got equally spaced equipotential lines. Okay, so what's the change in potential experienced by the charge? 0 plus kq over r minus kq over r plus 12 volts minus 12 volts. Okay, so what do you think of that? And the answer is actually very straightforward. The charge went from minus 4 volts to plus 8 volts. It experienced a change potential of plus 12 volts. Final minus initial, plus 8 minus minus 4 is plus 12. Okay. Now this is a point charge we moved around, but the potential it experiences is coming from some other collection of charges. In fact, what it could be is there's a red thing at the top of the picture and a blue thing at the bottom. So it could be just you've spread positive charge uniformly on a cookie sheet, and then an equal amount of negative charge uniformly on a cookie sheet at the bottom. The positive stuff was at the top. That's a nice way to make a uniform field. We call that a parallel plate capacitor, which we'll get into next time, actually. Okay, so one thing you don't want to do is use the equation kq over r in this particular case. Now, the point charge itself produces a potential of kq over r, but this potential is produced by something completely separate from the point charge that we're moving around. Okay, it's produced by our, for instance, cookie sheets of positive and negative charge. Okay, so we've gone from minus 4 volts to plus 8 volts. Potential went up by plus 12 volts. Only use that kq over r equation when you're dealing with potential from a point charge. This is a point charge moving around in a totally separate potential. It's certainly not a point charge. Potential is moving in. Okay, here's our final question here. How would your answer change if the charge had been a negative charge instead? So we moved a negative charge from minus 4 volts to plus 8 volts. The potential difference it experienced would also be plus 12 volts, or would it go to minus 12 volts? Okay. And it doesn't matter what you're moving. You don't have to move anything. You just have to say, okay, between the start and the end point is 12 volts higher than the start point. Whether I'm moving anything around from the start to the end or not, the end and the start differ by 12 volts, with the end 12 volts higher. Now, something would change if you moved a negative charge versus if you moved a positive charge. What would it be? Well, it would actually be the potential energy associated with that charge being in that field. Okay, so here we got delta U is Q delta V. So delta V is the same for the charge, whether it's positive or negative, but then delta U is different in the two cases. Okay, it's a positive quantity for the positive charge in this case because delta V is a positive thing, and delta U is negative if the charge in our case is negative, because again delta V is positive. Okay, so there's some information about potential, and we'll try and clarify a little bit that stuff when we get to class. Okay.